So here's the basic rules for assigning oxidation state. Atoms in a free element have an oxidation number of 0. And this is true whether it's a monatomic metal or a diatomic nonmetal. Mg has an oxidation state of 0. H2 has an oxidation state of 0 also, because in its elemental state, it hasn't gained control and hasn't lost control of its electrons. The control is perfectly equal or balanced, whether there's one atom or two in its elemental state. Simple ions, so like magnesium ion, have an oxidation state equal to the charge of the ion. So if you see magnesium ion is magnesium 2 plus, then its oxidation state is also +2. In a neutral compound, your oxidation states have to add up to 0. And in a polyatomic ion, the oxidation states have to add up to the charge on that ion. So now, number 5, here's the rule we use most often, is the usual oxidation state for an element is the same as the charge on its most common ion. So that means for the A group, group 1A is usually going to be +1, group 2A metals are going to be +2, group 3A +3, group 4A ±4, depending upon whether it's a metal or nonmetal, group 5A -3, group 6A -2, group 7A -1. But as usual, it's the transition metals that give us some variety, and also a few of the nonmetals, the ones that are kind of clustered near the metalloid line: nitrogen, phosphorus, sulfur, tin, lead, and then your transition metals all tend to undergo different oxidation states. Think of those as being the flexible atoms out there, and they will adapt to whatever they're bonded with. So to sum up here, this is kind of the priority or the order that you want to determine oxidation state in. Group 1A and 2A metals are always going to be +1 and +2. There are no exceptions. So if you have a group 1A or 2A metal in your formula, go ahead and assign their oxidation state first. And then as far as nonmetals, fluorine, always -1. It is the most electronegative element, so it is never going to lose control of its electrons. Oxygen, nearly as electronegative as fluorine, so it's going to be -2 unless it bonds with itself, and then it can actually have a -1 oxidation state, or if it bonds with fluorine, and then it becomes a +1. So peroxides is when you have an O2 with a -2 charge, that means each oxygen only has a -1 charge. And when it bonds with fluorine, it actually has to become, it's actually going to lose control as fluorine gains control. Hydrogen, usually a +1, but when it bonds with the metal hydride, the hydrogen is more electronegative than the metal, so the metal actually picks up a negative oxidation state. Chlorine, -1 is its usual, but if it bonds with oxygen or fluorine, which are stronger and more electronegative than chlorine, then chlorine's going to become the positive or have less control. So let's look at some examples and see if I can help you make sense of this. HgCl4. Determine the oxidation state for each element. It says, hint, assign oxidation states to the easy to predict elements first. So the element that's easy to predict here is chlorine, because it's going to be -1 unless it has oxygen or fluorine bonded with it. So if chlorine is -1 and there are 4 of them, that means the one hydrogen has to have a charge of +4 so that this adds up to 0 overall. So what that really is telling me is that mercury has lost control over 4 of its electrons, and each of the chlorine atoms has gained control of 1 electron. NO2. Nitrogen is one of those flexible ones, so I want to save that for last. So I'm going to go ahead and do the O2 first. Oxygen tends to have a -2 charge to it, unless it's with fluorine or bonded to itself. So if it's -2 and there's 2 total, that means there's a +4 oxidation state for that nitrogen in order for this to be a balanced compound, because I've got +4 times 1. Let me try that again. My stylus isn't working quite as slick as I'd hope. So I've got +4 times the 1 nitrogen, plus I've got the -2 times the 2 oxygen, and that gives me an overall charge of 0. Au all by itself, 0. Now we go into a couple here with 3 elements in it. Same process, Na2SiF6. Well, I've got 2 in here that never change. Sodium's always +1, fluorine's always -1. So if I look at that, I've got a +2 and a -6 from those 2 elements, which leaves me with a +4 for the silicon. Zinc nitrate, NO3 is a polyatomic ion which has a -1 charge, so 2 of them is going to have a -2 charge. So I know zinc has to be +2 to balance that. As far as the nitrogen, 1 NO3 has a -1 charge, and I know that 3 oxygen each have a -2 charge, so oxygen has a -2 charge, total of -6, but only -1 on the ion, so that means my nitrogen has to be a +5. Magnesium and phosphorus, magnesium has to be a +2. If I have 3 of them for a total of +6, that means my 2 phosphorus each have to be a -3. And as I scroll up here, Na3PO4, Na is +1, times 3 is a total of +3. Oxygen's -2 times 4 is a total of -8. That means my phosphorus is going to be the other +5. Again, think about what that means. It means 4 oxygen have gained control over 2 electrons each, or a total of 8 electrons. And those 8 electrons have come 1 from each sodium and 5 from the phosphorus. H2O2, this is a case where hydrogen is going to be +1 for a total of +2. And I have 2 oxygen that have to tally up to a -2. So that means each oxygen is a -1. This is a case where oxygen is bonded to itself as peroxide. ClO3-, I've got 3 oxygen with a -2 charge each for a total of -6. I have a -1 charge on the ion, so that means my chlorine is a +5. So when you see an oxidation state, when it's already signed, remember a positive number indicates there's been a loss of control over 1 or more electrons or part of an electron, and a negative number indicates there's been a gain of control. So an increase in oxidation state from reactant to product shows the element is actually losing control, because remember, an increase in oxidation state means it becomes more positive and it's losing control or is oxidized. A decrease or a reduction in oxidation state shows the element was reduced or is gaining control. If the oxidation state remains the same, and that can happen, it just means that atom wasn't involved in the redox process. It's what we think of as like a spectator ion. So here's some more examples for you. Decide which species is oxidized and which is reduced. Well, to do this, you have to decide, you have to know what the oxidation states are first. So here's the example I had mentioned back in the first video with hydrogen and oxygen forming water. So if I have H2 and O2 in their elemental form, these each have an oxidation state of 0, but when they form H2O, oxygen is going to take the oxidation state of -2. That means each hydrogen is +1. So hydrogen went from 0 to +1. That means it was oxidized. We saw an increase in its oxidation state. It became more positive, less control. Oxygen then better have been reduced, and I do see that it went from 0 to -2, so I know it was reduced. It gained electrons or gained control of electrons. Ca plus SN2 plus Ca2 plus Sn, so these metals are just 0. And I can see that calcium went from 0 to +2. That means it was oxidized. Tin went from +2 to 0. It was reduced. Third one's a little more complicated. I've got hydrogen with a +1, so that means nitrogen's a -3. It's gain control here. Oxygen's 0 since it's in its elemental state, but on this side it's -2 in both of these compounds. Hydrogen's still a +1, so hydrogen's not involved. Nitrogen has now become a +3. So nitrogen has gone from -3 to +3. It's been oxidized. If I can spell oxidized here. It's been oxidized as it's increased by 6. So it's apparently lost control of 6 electrons. And then oxygen has gone from 0 to a -2 and has been reduced. Last thing to mention is oxidation number versus oxidation state. It's a very technical difference, the difference in these two terms. But because transition metals have more than one common oxidation state, the name, when you read like copper 1 oxide, they will give a Roman numeral in parentheses to show what the oxidation state is. Technically, this Roman numeral is the oxidation number, and then oxidation state is what we assign when we look at the examples down here. And I know that the oxidation state of oxygen is -2, so if I have 2 copper, this is +1. This technically is the oxidation state, whereas this is considered the oxidation number. The terms are used interchangeably by many, many people. Copper 2 oxide lets me know that here it's a +2 to oxygen's -2. So write the names of the following compounds. If I give you Ag3PO4, first of all, you should know silver's always a +1 oxidation state, so that's a poor example. But PO4 is a polyatomic ion with the -3 charge. If I have 3 silver to share that -3 charge, then I could write this as silver 1, it's a 1 there, phosphate. Although, again, silver generally isn't written with the Roman numeral because it's always known to be in that +1 oxidation state. The cobalt chloride here, chlorine has a -1 oxidation state, and if there's 5 of them for just 1 cobalt, I can assume cobalt has a +5 oxidation state. So I'm going to write this cobalt, use the Roman numeral V, chloride. And then Fe2O3, if oxygen has a -2 for a total of +6, then I have 2 Fe to share or to lose those 6 electrons. Each Fe must be a -3. So this would be iron 3 oxide. And then going the other way, write the formula for the following. Well, if manganese is a +4, oxygen's a -2, I would need MnO2 for manganese oxide, really common oxidant in redox equations. And chromium 3 oxide +3 and a -2, so this would be Cr2O3.